Good day, everyone. So today let's take a look at some items related to introductory organic chemistry. And we're going to just go through several topics, draw some things, and also show certain chemical reactions. So let's just call them items. So then we're going to start with item one right here, which is going to be about the conformation of alkanes, right? So previously we were looking at the situation, for example, we had, let's say, some sort of molecule such as butane, right? So it would look like this. So as you can see from the skeletal drawing, so we have one, two, three, four carbons, right? So, and then from the visual perspective, that's what this molecule looks like. That's the way it can be drawn. However, what could happen sometimes is the so-called conformations can change, right? So, and then they can change because of the rotation of parts of the molecule about certain bonds. Let's consider this bond right here. So this one in the middle between carbons 2 and 3, right? If we were to name carbons like 2, oh, sorry, it's not 3. So let's say 2 and 3, right? 1, 2, 3, 4, 4 carbons total. So what could happen is that we can, so to speak, grab this molecule by carbon number 1, right? And then we can rotate this bond sort of upwards, right? So, and then the rotation will be happening around or about this bond kind of that way or the other way. So I think it's going to be going from here to here. So this carbon number 1 will go upwards, as you will see in the next drawing. So we're going to go approximately in this direction, right? So then this bond kind of like remains static. There is no rotation about this bond. So the rotation about this bond between carbons 2 and 3 will be happening. As a result, we are going to have the conformations, so which are kind of interchangeable because the rotation is free about bond 2 and 3 between carbons 2 and 3. And as a result, what we're going to obtain is going to be looking something like that. So this is carbons 2 and 3. They will stay. That's your 3 to 4 bond. So 2 is here, but then carbon number 1 will end up being here. So that's carbon number 1. So you see, that's what changed. So the position of carbon number 1. So we kind of grabbed carbon number 1, and this is our kind of like thing that is going to move, right? So, and then this, the rotation about the bond 2 to 3 happened, right? So if I want to, as a result of this rotation, the carbon number one is now on the top, right? So then if you can see, so there is a difference between those two structures, right? So at this point, so if let's say we imagine some sort of continuous line going through points or carbons 2 and 3, it's going to be looking like that, right? So let's say it's going to be our continuous line, some kind of like plane, or just like dotted line at this point, right? So now this dotted line preserves in our second conformation on the right-hand side. What changed is that previously we had carbons 1 and 4 on the opposite side of this imaginary dotted line, right? But right now, once this rotation happened about the bond 2, 3, let's call it this way. So now we have carbons 1 and 4 on the same sides relative to this dotted line. Opposite sides, same side is a very popular notion that we will see later in organic chemistry. So it's going to be a good idea to start getting accustomed to this notion, same side, opposite side. So funnily enough, this notion even got special terms from the German language, which would be respectively entgegen, which means against on the opposite sides, and zusammen, which means on the same side, right? Kind of like two, like together, or something like that, right? So yeah, basically that's what we're going to have here. So the rotation about the bond. So if I were to show this from another perspective, right, because it might be like beneficial to look at those conformations from the model model creation point of view. So let's create this model, right? So the first model here, let's call it like A, for example, right? So this conformation officially is called a chase looking conformation, or not chair, just chair looking conformation, or in our words, it could be looking like a beach chase, right? On which you lie when you're on the beach, acquiring some sort of like sunlight and vitamin D, right? So this looks like a boat, right? So to some extent looks like a boat. Sometimes it's called a tub. So, but yeah, the shape is different, right? For conformation B, let's call it this way. So here we go. That's going to be your chair conformation, right? And let's imagine that we have it like that, right? So this is going to be our carbons 2 and 3, for example. Trying my best to kind of like make it similar to what we see on the whiteboard. So, but imagine, so those middle carbons will be carbons 2 and 3, for example, right? So 2 is kind of up, 3 is kind of down, right? Then we have carbon number 4 up, 1 down, right? And then overall we have this good looking chair or beach chase conformation. So now we're going to grab this carbon number 1, which is presumably number 1. So that's a kind of like the one which is kind of looking down in conformation A on the whiteboard. And now we're going to do the rotation about the bond 2,3. This is bond 2,3, and then stuff is going to rotate about this bond. So you see that's the bond, which kind of is represented by my index finger, and the rotation about this bond or around this bond is happening, right? So as you kind of like have this carbon number 1 right here. So let's remove this as well. So like make a more proper butane looking molecule. So only 4 carbons now. So carbons 2 and 3. So bond 2, 3. So now the rotation will be taking place. I'm going to grab carbon number 1 and I'm going to rotate it upwards about bond 2, 3. Now it goes downwards back to conformation A. Now forward to conformation B. So now you see this is conformation B. That's carbon number 1, 2, 3, 4 is here. So it kind of like stays, right? And now we have the tub looking conformation, or boat, I think, in other terms. So boat or tub. So now the rotation about bond 2, 3 takes place. So up, down, okay? So now you are back to the beach chase or chair conformation. So something along those lines is happening in the like actual molecule, except here we have the macro scale, right? So this is our butane, and this is like its chair conformation versus its boat or tub conformation. Beach chase, tub. Okay, so now, is it kind of going to be the same molecule? Yes, it's going to be the same molecule. We are not making any isomers because of this rotation that leads to creation of different conformations. Why is that so? Because the structure still stays the same, right? It is basically the straight chain of 4 carbons. Here we have also kind of like the continuous straight chain of 4 carbons. Well, technically they're not straight, right? So this one is a kind of staggered sequence. So here we have kind of like up, down, down, up sequence, right? But overall, this is just the continuous chain of 4 carbons. And what we also do is that we don't break any bonds to make the new molecules. We don't make any isomers because we don't break any bonds. If we want to make the isomers, so like we can do that, but you see what happens? So that's the key difference. So right now we just do the rotation, right? So the compound stays the same. It is just rotating, right? So what if it's going to be like in this weird conformation, right? So kind of like in between the tub and the chase. So it's going to be something like that, right? So this is still butane, just a different conformation, which is kind of like frozen in the middle somewhere. What if we're going to go maybe just a little bit, like small angle, right? So you have here now those 2 carbons straight opposite to each other. So all the 4 carbons form one plane, lie in one plane. But now we have the rotation by maybe like 45 degrees or something like that, right? So then this is still butane, but it's going to be just some kind of like slightly different conformation from this conformation. Conformation B prime. Okay, so like small difference, but the compound stays the same. It doesn't change. So this is still the same compound. It did not change because the bonds were not broken, and the building blocks of this compound, which are CH, CH2, CH3 pieces, and so on, are not rearranged, right? So this is just still the continuous straight chain. So now, if you want to make the isomer, like now let's get to item number 2. So we are going to get to isomers here. So it's gonna be something like that. So now we're going to like take a look at butane, right? So that's your 4 carbons in the straight chain. So, but now we're going to make the isomer out of that. So now it's going to be like not rotation, right? So, but we're going to do that. So that's a key difference here. What did I just do? I broke the bond to rearrange the pieces, right? So I cannot have like 2 compounds, right? Because it's not going to be the like isomer anymore. So we need to still have the same like single molecule, right? So we need to have the single molecule as a result, but with a different arrangement of building blocks, right? So that's how we can describe isomers. So now this kind of like carbon goes to the, so to speak. So if it's our 4th carbon, we kind of like detach it from the 3rd carbon, and now we're going to connect it to the 2nd carbon, right? So now we have a different molecule. See, visually it looks different. It's not just a kind of a continuous chain of 4 carbons, right? So now we have the longest chain here comprised of 3 carbons, this way or that way, 3 carbons. No matter how you look at that, there is no 4 carbons in a sequence, right? And then we have another carbon, the 4th carbon, like attached now to the 2nd carbon. So you see, it looks like a Mercedes-Benz star or something like that, right? So whereas previously, your isomer, like number 1, let's call it this way, for the lack of the better word, so, or just this compound, it looked different. It doesn't look like a Mercedes star. It looks like a sequence of just like 4 connected continuously carbons, right? So that's it. So this is your like isomerism versus conformation things, right? So now let's try to draw them. Ultimately, we'll have to draw those structures on paper as well as making them, right? So it's going to be something like this. So like isomer number 1, which is going to be CH3, CH2, CH2, CH3. And then on paper, they also do look different, right? So just kind of ask yourself, is there any difference or are they the same, right? So it's kind of like boils down to some extent to those like questions which we were asked way back in the day. So in some classes, okay, like find the differences between those 2 shapes, right? So they kind of like test your skills to find the differences, right? And then now we use those skills of finding differences in this particular course. So how exciting. So it's going to be a little bit of the sort of echo from the very past, maybe from the 1st grade, when you were asked such questions to find difference between like 2 pictures, right? So that skill is important, believe it or not. So not only at like 1st grade, but here as well. So now let's take a look at the isomer, right? So we just decided to rearrange now the building blocks. We broke 1 bond and then we made another bond. So now we have the isomer CH3. Let's say we have here CH, CH3. You see shorter chain already. So like I see the differences, or you see the differences as it's drawn in front of you, right? And then CH3 here. So now count the carbons, 4 carbons, count the hydrogens. We have 10 hydrogens, right? So here, oh, I made a mistake, by the way. I'm going to correct it. Okay, so now it's all good. So now count the carbons, 4 carbons and 10 hydrogens. So the molecular formulas are the same for compound A, let's say, and compound B. So now these are not conformational, it's kind of like conformationally different compounds. There's no different conformations. These are different isomers, right, of the same compound with the same molecular formula of C4H10. C4H10, C4H10. Molecular formulas are the same for compounds A and B, but their structural arrangement, if you will, is different. So just a continuous chain of 4 carbons. This is a continuous chain of 3 carbons with a substituent, right? By the way, so if you were to use your professional terms, newly learned, it's going to be the substituent, carbon-based substituent, such as methyl, is attached to this second carbon here, so which is going to be CH, right? So since it has 3 carbon-carbon bonds, now it can only attach one more hydrogen to itself, unless other atoms are required in the structure. So we assume that we can only kind of like compose our hydrocarbon from carbons and hydrogens, right? Fulfilling the valences of hydrogens and carbons. So tetravalent carbon, check. 1, 2, 3, and fourth bond between C and H. 1 carbon-carbon bond, 3 CH bonds. Same here. 1 CC bond, 3 CH bonds. 1 CC bond, 3 CH bonds. Okay, so again, we can draw it like so. That's okay. So if we have our like fundamental knowledge, that's why the fundamental knowledge is important, because it will carry over and will help you communicate more efficiently in the kind of like newly learned knowledge, right? So here, if you know that hydrogens are monovalent, so then you would kind of like know that even though this is drawn the way it's drawn, so it doesn't mean that all of a sudden somehow magically hydrogen has like the bond between carbon itself and another carbon, right? No, those 3 hydrogens are only attached to that carbon and this carbon only, and that's it, right? And this bond is implied to be between carbon and this carbon, even though this hydrogen is on the way, just like for the matter of drawing. Okay, so if you want, you can redraw structure B like this, right? So CH3, CH. So if you want to be more explicit about your carbon-carbon bonds, you can exercise some flexibility, so that's okay. So if that kind of like makes you like comprehend better this stuff, then you can draw structure like B prime, right? So that's going to be ultimately the same kind of like 3 carbon chain, right? 3 carbon alkane chain with an alkyl substituent, right? Carbon-based substituent, such as methyl. So, okay, great. So these are our isomer examples. So now we're going to move on to drawing perhaps longer carbon chains. Why? Because we are going to get a little bit more experience of drawing properly those carbon chains. So this is gonna be looking like that. So now let's just, and then also we're going to recall and get used to the names, right, which are pertinent to alkanes, depending on how many carbons there are in the chain for a particular alkane under consideration, right? So what we started with is that we were looking at the carbons that would contain anywhere from 1 to 10 carbons in the chain, right? And then, yeah, potentially we would see 10 new names for those respective organic molecules. The good news is that those names are based on the Greek language and Greek numbers. So potentially you have seen those names already somewhere in other science courses, and then this is not a completely new piece of knowledge, right? So, but now let's take a look at the carbon. So that contains, or like alkane, with the 8 carbons in the straight chain, no substituents, no functional groups of any other kind, no nothing, just pure alkane comprised of 8 carbons, right? So in the straight chain. So straight continuous chain of 8 carbons. What would that be called, right? So let's try to draw that. So again, if we want to draw that, then again, we'll need to recall some sort of concepts, right? Such as arranging the carbons in this kind of staggered way, right? We're going to arrange 8 of them, right? So 1, 2, 3, 4, 5, 6, 7, and 8. Okay, here we go. So this is gonna be our connection right and there, right? So now what are we going to do next? So we have here 8 carbons, right? So this is gonna be our chain or skeleton made of carbons for the molecule known as octane. So here we're going to now just beef it up, so to speak, with hydrogens, right? So we also will recall that carbons are supposed to be tetrahedral, right? So this will kind of be reflected in our drawing to some extent, which will be looking like that, the drawing of the bonds that emanate from the carbon atoms. Okay, so that's the ones. And now we're going to add hydrogens, which will be like this. So here you can also match kind of like this structure with the general formula, which is CnH2n plus 2. If you have, let's say, n carbons, such as 8, then the number of hydrogens will be 2n plus 2. 2 multiplied by 8 plus 2 is going to be what? 16 plus 2, 18 hydrogens, right? So if we know the number of carbons in a typical alkane, we can calculate the number of hydrogens, right? So just like double check yourself. So if I have 8 carbons in the alkane molecule, not cycloalkane, but just alkane, right? Then, or some isomeric alkane still, then I need to have total of 18 hydrogens, and you count them here, right? So make sure that you are like all set. So all the valences are fulfilled, right? Carbons are tetravalent, hydrogens are monovalent, and then here we have kind of like the 4 bonds sort of engaged into bonding with various atoms, right? So, well, not so much of variety, just carbons and hydrogens, to be honest, but still some variety is present here. So yeah, this is our octane molecule. So now, just like for the fun of things, we can try to make an isomer from that. And then maybe let's make an isomer that would contain only 5 carbons in the chain, right? So let's call it like isomer number or isomer A or something, right? So now we're going to make isomer number B, which is going to be looking like this. So let's just make sure that we have 4 carbons in the longest chain. Well, we can do that. So that's our 5 carbons in the longest chain. 5 carbons, right? So, but we're going to make the isomer. So we must not lose all of a sudden 3 carbons, right? Just because the longest chain contains 5 carbons. So what, right? So we should not forget that we can rearrange pieces, and then we can use the power of so-called substituents. So now you can have the carbon-based substituents, which, for example, could be just 3 methyl groups attached to those respective carbons for which I just have shown the bonds, right? So let's show the carbons here. So now you have your 8 carbons, right? You are in a much better shape. So even though, yes, you have the requirement now all of a sudden to have the 5 carbons only in the longest carbon chain, right? So 5 carbons. So, and then if you look at the connections, they will be represented by the bonds. So now you just need to add your hydrogens right here. So let's take a look. So right now all the carbons are connected. So, and now at this point, we just need to beef it up with hydrogens, right? But we need to make sure that we add the correct number of hydrogens dependent to the occupied already valences of the like particular carbon atoms, right? So here we go, right? So for example, this carbon only has 1 bond so far engaged. So to this carbon, we can add 3 H's, right? And now we have 4 bonds total engaged into this carbon, right? Or on this carbon. So now this carbon here is very different, right? It has already 3 bonds engaged by virtue of the fact that it is connected to like 3 other carbons. 1, 2, 3. So CC bond, CC bond, CC bond. 3 bonds are occupied, right? So now only 1 more bond is left over. And then it's going to be CH here. So let's just make it this way. We're going to use now this was an expanded drawing, right? So, but now we're going to use the so-called condensed drawing. So it's going to be like this, right? So CH. Then we'll have another CH here. So CH again. And now here we have CH3, right? So ask yourself, why cannot I have CH2 here? Well, because one valence will be just like free, right? So like it needs to be connected to something. So then here we must have CH3, that's a terminal carbon, another terminal carbon, CH3, and that's it. So we are done. Well, not yet. So this is another terminal carbon here, or the substituent carbon, which will be CH3 again. So here we have our like biggest chain from 5 carbons, and we have here 3 substituents, right? So alkyl-based substituents or carbon-based substituents, as we can call them. So we will be unfolding the terminology as we go along, so like those words will kind of happen again and again. So this is our carbon-based substituent because it has a carbon in its structure, right? So it's carbon-based. So we have methyl here, methyl. So this CH3 piece is going to be called methyl, and another methyl. So then we have methyl on the like termini. of this compound, of this isomer B. So then we have CH pieces, which are called methynes. Methine, that's another kind of like term, right, for this particular building block. So yeah, again, so like the notion, right, so from the past of the connection between the like terms and the structures is manifesting itself again. So just like be aware that this is a good skill to have, to connect terms to structures, especially in like organic chemistry specifically. So now let's maybe take a look at some sort of molecules, such as maybe hexane, right? And then let's try to add some kind of like, just for review purposes, right? Partial review at least, some sort of substituents to that hexane molecule. So it's going to be item number 4 right here. So item 4 will look like this. So I'm going to draw hexane, for example, and for our now practice, which should become a little bit more challenging, we are going now switch to skeletal drawings, right? So we are going to show the dots for the carbons. So 4 dots, 5, 6. So that's going to be our backbone, which is made from the hexane molecule, right? But then this hexane will bear some new substituents, which we'll try to draw. And then maybe it's going to be a good idea for now, right? As it's drawn, maybe pause the video and then try to recall any non-carbon substituents, right? So, which we did have like in the table in one of our lecture presentations, right? So like maybe you'll recall some kind of halogens, right? So that which we can add like so. We just show the bond and then maybe we can show the chlorine here, right? So that is a very common substituent which happens to be present in organic molecules, right? So then we can show the Lewis structure and here we go. Then what else can we say about this thing here, right? So it's a carbon here, carbon chlorine bond. Carbon and chlorine have different electronegativities, which are like significantly different from one another value-wise. So this bond will be polar. So let's maybe make it like red, for example, just like in your worksheets, you are sometimes asked to, oh, show the polar bonds, right, or something. So yeah, just kind of like show them with a different color. Maybe you have like a red pen, pencil, whatever it is, just kind of like do that, right? So then you might have some kind of like other group, such as maybe like amino group, right? So maybe let's make it this way. So we're going to show another bond, which is going to be between carbon and nitrogen. Carbon and nitrogen also have different polarities, so it's going to be quite a polar bond. So, but now it's going to be not the carbon-chlorine bond, but rather carbon-nitrogen bond, right? And then we must attach two more hydrogens to make an amino group, right? So, and then nitrogen in amino group will be similar to the nitrogen in ammonia, and then this nitrogen will also have the two electrons in the form of the lone pair. So chlorine will have like 1, 2, 1, 2, 1, 2. So 3 lone pairs, 1 lone pair on the nitrogen, right? So now all of a sudden, let's try to like modify this CH3 and then let's maybe make it. So because now we can draw pretty much anything at this point, let's maybe turn it into the acid, for example, right? And then all of a sudden we have the amino acid, by the way, right? Some kind of like maybe unnatural amino acid with the chlorine also in its structure. So, but it's still amino acid because it will have the acid and amino group, hence amino acid as the term name. All right, so to show the amino acid, so we can use a couple approaches chiefly, but what's going to happen is that you can turn this into the explicit carbon, right? So even though you have this kind of skeletal conformation, so and now you are going to show the double bond, which is going to be signifying the drawing of the carbonyl group, which must be present in the carboxylic acid functional group total. And then we also must have the OH, right? OH, just like this. So now we're going to show the Lewis structures, lone pairs on the oxygens, 2 lone pairs. Okay, now we have different atoms that contain different numbers of lone pairs, so it's like good, right? So like for your review purposes, just try to kind of at least look at those functional groups in the table and then draw them yourself, right? Maybe another time you'll be like, okay, like what's the amino group it's supposed to be like, right? So without looking at the table, you can do the like active recall, right? So recall that and then draw that, or maybe draw it like on the whiteboard with your peers, right? Like teach each other. So that could be a useful skill down the line because you will be able to kind of like perform some tasks which would require you to like show and kind of like explain and teach something to others, right? But more on that later. So anyway, so here we go. This is our kind of like substituents that we sort of added, right, to our original just plain hexane molecule. That would be just a straight carbon chain consisting of 6 carbons, right? And then you would have the alkane. But now we have the substituents. Substituents substituted something, right, in the original alkane molecule, which was hexane. Looked like that. So 6 carbons, right? So nothing exciting particular. But now imagine that we used to have here, for example, CH2, but now here technically we have only that. We have CH, right? So basically what happened again, what's the difference, right, between two pictures, right? So here was the difference between, yeah, these two drawings, right? Very similar to pictures. We used to have couple H's here, right, on the hexane, on this like second carbon. So now we have only one H and chlorine instead of second H. So one of the H's was substituted with a chlorine group, and now we have the chlorine group as the substituent here. So like same logic applies here. Couple hydrogens, right? So one of them was substituted with an NH2 group. Now we have the amino group. So here we used to have CH3, right? So, but now essentially all the H's were substituted with double bonded oxygen, single bonded oxygen, and H, right? So again, substitution happened, and then we built eventually the carboxylic acid group from like this terminal carbon, right? So at this point, we just kind of like draw and enforce like various new groups, but strictly speaking, there are chemical reactions that will lead maybe in several steps, oftentimes in several steps. That's why it's called multi-step synthesis, right? When we synthesize some sort of like complicated molecule, like the one here on the top, from something more conceivably simple than the molecule on the bottom, right? So this one. So such as the molecule on the bottom. So this is a simpler molecule, the bottom molecule, just carbohydron, I mean hydrocarbon, right, as we may call it. And now you have something more difficult. Why? Because you have a bunch of different atoms and then kind of like building blocks and the bonding patterns in this molecule than the molecule on the bottom. So we went from a simpler, maybe several steps, maybe, I don't know, like 7 steps, right? And you synthesize the molecule on the top from the molecule on the bottom. From simpler, you go to something more complex. So yeah, now let's maybe take a look at the ionization. That's going to be another topic to take a look at because we have the foundation for that. It's going to be our item 5. So now let's consider that amino acid, by the way, right? Which contain the amino group and also the carboxylic acid group. So those groups can ionize. Typically, what we mean by that is the proton transfer in some form. Carboxylic acid, being an acid, would lose a proton, right? So let's take a look at the first case, which is going to be like acidity, right? Acidity makes a comeback in organic chemistry, just like it used to be in general chemistry, right? So let's take a look at some sort of carboxylic acid that we drew that would consist of a certain number of carbons, 1, 2, 3, 4, 5, 6. Let's say that's going to be 1, 2, 3, 4, 5, 6. 6 carbons, right? So now carboxylic acid will be looking like this. So it turns out that in carboxylic acids, and then if you kind of like get it like right once, then you can use it over again for various carboxylic acids, right? So that's a good thing about that. So you kind of like have like one pattern, blueprint example or something like that, and then it's like spread for like over many other compounds which are carboxylic acids, right? Or contain the carboxylic acid group. So here you go. So this bond is going to be broken, right? So which will be the proton donor. So why is that so? So you can also ask, okay, but wait, there is also CH bond here, right? So, but what happens is that the difference in electronegativities between oxygen and hydrogen is very high, as opposed to the difference in electronegativities between carbon and hydrogen. So CH bonds, because of this like small electronegativity difference, are considered non-polar, right? But OH bond has a huge electronegativity difference between O and H, and then it's considered polar. Polar bonds, consequently, are more easily broken, right? So, and then this is what we have here. So CH bonds will stay intact, but OH bond will ionize, dissociate, break, right? And then as a result, we are going to have something like that. So as you recall, or as you might recall, so the carboxylic acids are weak acids. So that's why when we show their dissociation, we're going to show the equilibrium sign. So we have our 6 carbons, all good. So let's like redraw some things, and then some things will be new. 1, 2, 3, 4, 5, 6. Carbonyl, oxygen, right? So then H. Okay, so now let's put the charges, right? And probably lone pairs as well. So there used to be 2 lone pairs only on the oxygen. So, but now we have this kind of like, let's show it in color, maybe red, right? Because why not? So here it is, red electrons that would comprise the OH single bond, right? 1 electron on oxygen, 1 on the hydrogen. So then we're going to switch back to the black ink, and then we're going to show the movement of this red pair of electrons towards oxygen, right? Just like that. So now both of those red electrons will be on the oxygen. So they arrive and the oxygen. So the other electrons that used to be there in the form of lone pairs stay. Just like that, right? So what also happens is the charges change, right? So we previously used to have the neutral oxygen atom even bound to an H, and then also neutral hydrogen atom even though it's bound to an oxygen atom, right? But now, so oxygen, for example, technically acquired this one extra electron, right? So the entire electron pair moved, or in other words, quite literally, this electron arrived at the oxygen. This like right electron arrived at the oxygen. And now, so if you just kind of like cover this part, H with the red dot, so you used to have kind of like originally the oxygen with the neutral charge, but now you add extra electron, or maybe let's make it, I don't know, like for the sake of explanation, let's make it blue, for instance, right? So blue electron on the hydrogen. Now it is here, right? So, and now you have the neutral atom of the oxygen plus extra negative charge from the blue electron. 0 and +1 charges now kind of like are added. You get a negative charge on the oxygen as a result, right? So let's show it this way. That's why you will have this like O minus sign, because oxygen acquired extra electron. On the other hand, hydrogen lost its electron, right? Now you used to have the like H with the blue dot, which is kind of just the neutral charge, neutrally charged hydrogen atom, but now it lost its blue electron, right? And then zero charge turned into the +1 charge. So basically neutral H atom with a dot. One negative charge is lost, it's out, then consequently the counter charge has to be produced, which is going to be +1. So 0 neutral charge originally. You lose one negative charge, then you counter produce, so to speak, right? The +1 positive charge. So that's it. That's why you are going to have H plus, right? So as a result of the like acid behavior or the proton donation. So yeah, that's like how carboxylic acids will kind of dissociate in general, right? So here we have just kind of like a specific example, but theoretically it could be like any other thing, right? For our intents and purposes, maybe it's going to be not 5 carbons in this chain, maybe it's going to be 16, maybe it's going to be 77, maybe it's going to be super branched, doesn't matter, right? So this carboxylic acid carboxylic acid functional group, right, which is going to be in this like other circle, will still dissociate in this like very fashion, right? Making those like 2 circles like for your reference. All right, so now let's take a look at the amino group, which could also be present somewhere. Let's draw some kind of like hexane, right? And then all of a sudden, let's imagine that there's going to be like NH2 group connected to the second carbon, right? So we'll show its lone pairs. So amino group is an example of the base group, right? So as you might recall again from the general chemistry, so this base will do what? So it will accept a proton, right? So that's the difference between acids and bases. Acids will lose or donate H plus, NH plus, and then amines, which are like bases specifically, will accept an H plus. So like bases are proton acceptors, acids are proton donors. Donation like this, right? So this is going to be now basicity. Basic behavior is exemplified by amines, for example, right? So what will they do? So they will accept H plus. Let's just add hydrogen plus or a proton, right, from some sort of proton source, right, whatever it might be. So that doesn't matter for us, but now we're going to show the amines are weak bases. So their like proton acceptance will be accompanied with the double arrow, right, or like a reversible reaction arrow. And then as a result, we are going to still have the product, right, which is going to be looking like this. So a lot of the organic chemistry is redrawing, right? And then some things have to change, right? Especially if it is a like ongoing, like feasible chemical reaction, right? Things will change in the molecular structure eventually. So we still have CN bond and right? So we'll still have H2. Now, what's going to happen is that pay attention to this lone pair. It can actually be used, it can become the covalent bond, right? So what do I mean by this? So this hydrogen plus here is devoid of electrons. It doesn't have any electrons, so it can accept electrons, right? So this nitrogen has like a bunch of electrons, which are unbonded in the lone pair form, so it can make the bond, right, theoretically. And that's what happens actually in the like actual chemical reality. So these electrons are shared to make a bond, right? So let's put a hydrogen devoid of electrons first, right? So now we are going to colorize the electrons. Let's maybe make them, for example, red and blue, right? Let's maybe make it like purple, right? So because why not? So let's imagine that like their equivalents, so for our like coloration purposes, they are different, just to kind of like see what happens, right? So in terms of the distribution of electrons. So I'm going to, let's say, leave this kind of like purple electron on the nitrogen, right? But then the red electron will end up being on the hydrogen, right? So, and now as a result of that, as you can see, so if you only connect those 2 electrons, you're going to form nothing more than a single covalent bond. So that's how this bond is formed by virtue of that lone pair. So yeah, the red electron ends up on the hydrogen, so that's like one way to look at that. But another way to look at that is from the arrow pushing perspective. So we can show the curved arrow like so, from where there is lots of electrons in the lone pair form to where there is no electron, right, on the H plus. So that's how the like arrow will be drawn. and then it will point from the electrons to like no electrons, basically, right? So this arrow, also in other words, shows the movement of this pair of electrons. And then technically this pair used to be on nitrogen only, but now it is kind of like moved to the area between nitrogen and hydrogen, right? So that's what we can kind of like explain. That's how we can explain this movement of the pair of electrons, right? So, and then specifically as a result of that movement, the like a red electron ends up being now on the hydrogen, right? And then together with the blue electron left over on the nitrogen, the HN bond is created. So also as a result of movement of that lone pair, right, the electrons are shared. Nitrogen gave its electron to H plus, and then H plus became H0, right? So have plus one charge. Then you have the minus one negative charge from the red electron, plus one, and minus one becomes, as a result, zero. Now you have H with a red dot, which is nothing more than H with a zero charge, right? Or the neutrally charged hydrogen atom, right? On the other hand, so you have nitrogen, which lost one electron. Nitrogen here used to be also like zero charge, right? So now it lost one negative charge, so consequently the counter charge has to be produced, which will be plus one on the nitrogen. So that's it. Now you have your like N plus because of the loss of the electron by the neutrally charged nitrogen previously. So now you have total charge here, 0 and plus one on the left side, total. On the right side, you have the total charge of plus one as well, 0 and plus one, right? So plus one charge. So charge-wise, you are all set, you are balanced, in other words. And then if you want to count the atoms of hydrogen, nitrogen, and carbon, in this case, then just make sure it's kind of the same on the left and right side, and then you are going to be in good shape. So that's going to be your example of the basic behavior right here. So at this point, I think it's enough talking, and then, yeah, just kind of like get to your personal reviewing, right, of the slides. Try to actively recall what you have seen. So if you achieve the point that you cannot recall, just go to the slides and then try to like maybe redraw those things in various forms. Perhaps you can go from the skeletal structure to the like fully expanded structure or condensed structure, or maybe from the expanded structure you go to the condensed structure, right? Try to draw some isomers, kind of like those things that I have just drawn. Think about a little bit like other building blocks, right? So because thankfully you have a lot of variety of molecules in organic chemistry. I think it's literally somewhere in like millions of various organic compounds, right? So at this point, like a good thing will be to use to some extent your imagination and say like, what if I'm gonna use maybe some molecule with let's say 4CH groups, like then 4CH2 groups, and how can I connect them together so that I would make some kind of sensible connections, right, in this molecule, not violating the balances of the atoms. What if I add some kind of like nitrogen containing group? What are those? How about oxygen containing groups? What are examples of those, right? So then you can like actively recall that. So like ask yourself the question and answer that. So that's your like active recall example. I think maybe like draw that on the whiteboard, draw it on a piece of paper to emulate the exam sort of approaches, and then hopefully you will be in like in a better shape moving on. So, but anyway, so that's enough talk, and thank you for watching. Bye, everyone.